meeting is being recorded.
All right, welcome everyone to the second code seminar of this semester. We have Antonio Bellon here, who will talk about time-varying semidefinite programming.
Thanks so much. Thank you for your invitation. I'm very happy to give this seminar, and also the pizza was a very nice way to start. So I will talk about time-varying semidefinite programming, which is the topic of my PhD, and in particular, I will focus on the geometry of the trajectory of solutions, which is the object of my first research that I was doing during the first year of my PhD. So I'm a candidate PhD at the Institute Department of Computer Science of FEL, like Faculty of Electrical Engineering, and I'm supervised by Jakub Mareček and Vyacheslav Kungurtsev, who are both researchers at the CTU FEL. And I'm also supervised by Didier Henrion, who's a professor at the Department of Quantum Theory of FEL, but also a researcher leader at LASI and RAS. So LASI is the Laboratory for Analysis and Architecture of Systems of Toulouse. So I will start by introducing what is semi-definite programming in general. And first, like a quick question: how many of you have heard about this semi-definite programming optimization? Okay, so like half of you. So just to summarize, I say that SDP is a class of convex optimization problems, which basically give you a generalization of linear programming and also second-order cone programming. And so this slide is like to illustrate graphically also. Maybe you are more familiar with linear programming, so you have to optimize a linear function subject to linear constraints and the request that your variable x is as all non-negative components, that is, x lives in the non-negative orthant, which is a cone in particular. So if you extend this notion of a cone and you switch from the cone of non-negative vectors to the cone of positive semi-definite matrices, you get a generalization of linear programming. So in linear programming, you see that everything is flat and it's nice, and SDP is the feasible set was given again by the intersection of an affine space with the cone of positive semi-definite matrices. So it's described by polynomial inequalities. It's as a more complex structure here. I'm showing you the so-called Cayley's spectrahedron. But the objective function is still linear. So why is it, or where you can use SDP? So first, I'll start with an example from combinatorics. So one of the first application of semi-definite programming was in the Max-Cut problem, and Gummans and Williamson provided this algorithm, which is under the unique games conjecture, which maybe you are more familiar than I am. If this is true, it can be proven that this algorithm is the best polytime algorithm, and it provides at least 0.88 optimal solution. And the idea there is that you can cast the Max-Cut problem as a quadratic polynomial problem, and the idea is that you can relax this problem and going from this non-convex problem to semi-definite programming, which is again a convex class of optimization problems. And there are other applications like in control theory, when you can certify some properties of dynamical systems, even in machine learning. Very natural applications arise in statistics, where, well, because of the covariance matrix needs to be a semi-definite matrix. There are even applications in signal processing. But I would like to talk a bit more about applications in polynomial optimizations. So I will talk briefly about this Lasserre's hierarchy. So Lasserre is actually a researcher in the same lab of Toulouse that I was staying before. And so he developed a hierarchy of, let's say, a procedural algorithm to solve polynomial optimization problems. So a polynomial optimization problem is nothing but the problem of optimizing a polynomial function subject to polynomial constraints, like inequality there. And what the idea is that with you can approximate the solution of these problems with a hierarchy of increasing size STPs. So basically, you have you start with a semi-definite optimization problem that is providing you with a relaxation of your original problem, and then if you increase, in some sense, the size of this problem more and more, then you get closer to a better approximation of the solution of the system. And here the key idea is that basically you can recast that problem as deciding whether a polynomial is non-negative, and then you know that a sufficient condition for a polynomial to be non-negative being a sum of square. And the trick is that deciding whether a polynomial is a sum of square, you can actually cast this problem as an STP. And then you can also use some standard conic duality properties. But the key takeaway here is that this procedure, under my assumptions, actually guarantees that there is an order of the relaxation at which the relaxation is exact. So you really solve the original polynomial problem, which can be quite a hard problem. And yeah, so and you approximate the solution with increasing quality. So I mean, I think this is a quite remarkable application, and can tell you why STPs can be such an interesting class of problems. But in my case, I focus on time-varying semi-definite programming. So it's still like the same problem as I described before, but the data of the problem now depends on a time parameter t. So I'm studying the dynamical version, say, of the problem. So there has been some work done before on this. This was one of the first reference where Goldfarb and Scheinberg started studying a parameterized version of STP. And then these are the most maybe recent applications. Okay, I think I won't get in detail here, but I will tell you the initial aim of my PhD was actually to address or study the trajectory of solution to time-varying STP. So I'm talking about the trajectory because if the problem is non-time dependent, so if time independent, then your solution, you can imagine, is a point. If you add some time dependence, then this point can start moving. So you have a trajectory, and we want to geometrically kind of study this, what can happen to this trajectory, and then classify basically what are the regular behaviors that can then arise. So this was the aim, and this is what I would talk today. So this research resulted in a paper that is available on arXiv, where the contributions were first defining six type of points in the trajectory. So you have this trajectory, you select one point, and then according to what happens at this point, you classify this point in some types that I will describe. And then furthermore, we proved this classification theorem, proving that only these 6 of points can appear. So there is no other possibilities. And actually, if you under some more assumptions, there are only 3 of these types of points that can arise. And so this is useful. This knowledge is useful because, well, basically we know what can go wrong, and this is important. So if you want to design algorithms to solve trajectory, you want to know what happens to this trajectory, if it's smooth, when smoothness is lost, and so on. And then this, thanks to the Lasserre hierarchy that I was describing before. When you start considering time-varying polynomial optimization problems, then this research can be also useful for that. So I will briefly give you a crash course on the properties of STP. I will describe the 6 type of points and show you this classification theorem, and maybe I will give you a sketch of the proof if we have time. Okay, so if you are familiar with optimization, you know that you always have this nice thing called duality, and you usually want to always look at both pairs of problems. So here you have the primal STP, and on the right you can see the dual of that problem. For a given STP, we have a set of first-order optimality conditions. that are in general they are sufficient for optimality. So if you find some two matrix xz and also vector y such that these conditions are satisfied, then x and z are solutions of these two problems. And then it's well known that if this strict feasibility is satisfied, which means basically, like intuitively, it means that the feasible regions of both the primal and the dual have an interior point. So this is more like a technical condition. Under this condition, these conditions here are actually equivalent to optimality. So you really want to look at those. Okay, so these are other, like, let's say three properties that that are required to like kind of study this type of problems. So the question that I would like to address, let's say now, is how do we know that a primal dual solution for the pair of semi-definite programs is unique? So I will answer to that, but first I need to define these three properties. So strict complementarity basically just says that the rank of the two solutions x and z sums up to n, where n is the size of the problem. And then you have these non-degeneracy properties. They are more like technical. So A is this operator that defines the affine space of the that gives you the feasible set. And by Matkal tau, I'm referring to the tangent space of the manifold of matrices that has the same rank of x or z. Okay, but I don't want to go in detail like and describing what are these conditions exactly. But what you should know is that so if you have primal non-degeneracy, then you have the dual problem is unique, and also the converse. Like if the dual is non-degenerate, then you have a primal unique solution. And then under strict complementarity, so this is the first property. These are actually the equivalent here. And a nice insight is that if you take a generic SDP problem, then it will satisfy these properties generically. So this tells you that in general the solution is unique. But then, of course, there might be the cases in which this is not happening. And okay, I will just quickly go through this. So this is just to give you more insight on why these properties implies the uniqueness. And basically the thing is that if you can rewrite those optimality conditions as a function f, like that, and then basically you want to look at the zeros of that function. And basically if those properties hold, then the Jacobian of the function f is invertible at the points you are considering. So you can basically invert and find the unique. There is a unique point such that that function is vanishing. Okay, now just remember that we went through some properties, but we want to study some objects related to the time-varying semi-definite programming. So basically, you can define the primal and dual feasible sets, and these sets are depending on parameter t, so they are actually set maps. So for every value of your parameter t, you have some different set that describe your feasible sets. You have the optimal values, of course, and then you have what we are interested in, so the optimal set maps. So for each value of the parameter t, we're interested at the behavior of the optimal set, so the set of optimal points, which again, in general, is unique, but it can be that it's also it can also be not unique. So that's when tricky things can happen actually. So again, this here I'm starting like what's the goal in a way of this talk is basically I want to take a point x star that belongs to the optimal set at a given time, t star, and then I want to classify this such a point. And so basically, our approach consisted in considering a trajectory of solution where, like, let's say everything is going right. So you have this point is describing a smooth curve, and then we ask, okay, then let's stop, and okay, now we allow for everything to happen. What can happen? So the first question was actually how can we know, how do we know that the point is actually behaving in a smooth way? And then the answer would be, again, the same properties that I was describing before. And the keyword here is the implicit function theorem, basically. You can use that to prove this smoothness. But then the key or more interesting question was how this good behavior can be affected. And this resulted in defining, well, you have a regular point, which is when everything is going fine. And then you have 5 other points where there are things happening. So briefly, I will describe the assumption that we are taking. So first, we assume that the matrices that define this linear operator A are linearly independent, or in other words, this linear operator mathcal A must be surjective. And then we have also some assumption on the uniform boundedness of this operator and its semi-inverse. And then we require strict feasibility of the problems, and it's a dual for every value of the parameter, which is a quite standard assumption. And we ask a very weak assumption on the parameterization. So we require that the data are continuous function of the time. So these are the assumptions, and now I'll start defining what can happen in time varying STP. So first, as I say, like you can see here, it's just an example, like you have a regular curve. And now I give you an example of when this happens. So now let's say that our feasible set is the Cayley's tetrahedron, the one that I showed you at the very beginning of the talk. And then imagine that you want to optimize a function that can be pointing like in this way, and then starts moving a bit like that. So the solution will basically move along this blue curve. And since it's moving on a smooth surface, it will give you a smooth curve, and which is really like a curve. So it's really a unique point moving basically, and it's again it's a differentiable point. So the first thing that can happen is that actually this differentiability can be lost. And here again the same example. Well, you can imagine like the opposite thing, like maybe an objective function and it's going like this. So I have a point that is like moving with like, let's say, constant velocity, and then at some point it stops suddenly at this vertex here. So basically you have a loss of differentiability, and this is actually, you know, if you want to use some algorithm to track this trajectory, and you want to use local information, you know, like here there are bad things that could happen, because if you don't know what happens here, you will, you know, you want to go up, and this is not true. So you have to be careful. Yes. And another thing that can happen is that you have what we defined as a discontinuous isolated multiple point. So there is a point in the trajectory where suddenly you don't have a single optimum, but you have a whole one-dimensional segment. And again, here, same example as before. You can imagine you have a point here that is moving on the surface, but here this is basically an edge of your spectrahedron. And then when your objective function is pointing like upwards, then your optimal set is the whole segment. This can happen, but another way in which can happen is, again, imagine same objective function rotating like this. So you are moving like this, you reach this point, but then when you're pointing downwards, you have the whole segment. And as soon as you move, again, counterclockwise, or clockwise, you will get this other vertex. So I described the same type of point, but you can see there are some difference in that, well, you can geometrically see what happens in these pictures here. So the idea why they're different, because basically here, morally, you can somehow, if you're tracking the solution and you're using local information, you won't even realize that something is happening here, or nothing will go wrong. But here, it's really like more a discontinuity. So this is a more like dramatic loss of continuity. But we decided to put them under the same name. Then what can happen is actually that this loss of uniqueness is non-isolated. So instead of you just have an instant in time where this happened, you have a whole interval of time where you are losing uniqueness. And this again, I can provide you examples to this. Like here, I have the same example as before, but I kind of cut it with the hyper outplane, outface the spectrahedron, and saying this same reasoning, like you are moving like this, then you can see that the solution will be stuck on this edge for a whole positive some interval of time. So these are all. No, wait. There is also another type of degenerate behavior, which is like a bifurcation, or we call it like a continuous bifurcation, in which what happens is that you are still losing uniqueness like before, but this happens in a continuous way, where the continuity notion that you're using here is set valued from the continuity notion. But so here continuity is somehow preserved, but still you have something degenerate happening. So we wanted to distinguish between these two situations. Okay, then finally, these were kind of situations that when I was studying, I was expecting to happen. And then the question was, what else can happen? And you can think about it. It's and then the answer was that this is really like the degenerate thing that it's just what is excluded by all the type of points that we discussed, is basically that around this point T star that you're considering, there exists like a sequence of points, decay, such that something bad is happening in all the neighborhood at all tk. And what can happen is either a continuous bifurcation or a loss of a loss of inner semi-continuity is basically this case here. Something like that is happening. So here you have an example where you have a sequence of point tk, and each of tk points is a continuous bifurcation. And you can easily produce such examples by just here I have a very small example where just putting some trigonometric parametrization, then this happens. So this is basically the type of point that completes the picture. So and what I proved is that under the assumption that I was showing before, there can only be these 6 type of points, and then if furthermore there exists a time that is non-singular, and I basically I won't tell you now what the non-singular is. It's a property. If this point t hat is non-singular, then in the whole parametrization actually only 3 type of points can appear. So the regular one, and then there are only the non-differentiable case or the discontinuous isolated multiple points. And if you look at what these were, are basically cases in which the degeneracy only happen as at a single instant of time, right? Like here or here. Whereas here, for example, the uniqueness, the non-uniqueness is happening for a positive amount of time. So the first part of the theorem is kind of almost trivial, but it's basically based on a case partition. So you want to give a logical partition of all the possible scenarios, and then say that in each scenario only the types that we describe are possible. And basically the first you start with a partition where you say that at the time you are considering your optimal set is given by a single point or a multiple point. And then you have another partition according to what happens afterwards. And then you combine these two partitions in 6 cases. And you can see that in all 6 cases, you can only have the type of points that we defined before. So this is basically like almost a game you can play. And then you can see that the last point, that is the last type of point that is the most degenerate behavior, follows from the fact that 1 and 2 are not completing the picture. So you can have some left or right neighborhood of t hat where your solution is single valued, or you can ask that in this neighborhood the trajectory is all multi-valued, but then there is somehow the third case to negate the previous two, which then create this what we call this irregular accumulation point. Then yeah, this is the the proof of the other part of the theorem, of the second part of the theorem. But maybe I will, so there will be 2 lemmas, but maybe I will just focus on this one, because again, it's related with what I was saying at the beginning. So if you have a co-pair of time-varying STPs with the properties that at a certain t hat, these 2 properties of strict complementarity and primal Bellon degeneracy are holding, then basically you know that there is a unique and continuously differentiable curve, both in the primal and dual space, defined on some neighborhood of t hat, such that this curve is it's giving you the unique and also strict complementary optimal solution. And again, the proof is basically given from the fact that the KKT conditions are kind of necessary and sufficient under our framework to optimality. And if these 2 properties are holding, then the Jacobian of this function is invertible. So that basically you can apply the implicit function theorem and have a properly defined curve around it. But then you also have to include this thing here, because I mean, there is a curve that satisfies this, but you don't know if it satisfies this. But then since you know that this solution is unique, if if this unique solution of f equals 0 is not satisfying this inequality here, then it means that the problem is infeasible, and this contradicts the hypothesis that we are setting on the problem. Yeah, and then there is this more technical lemma that was proven by John Auenstein and others in one of the 3 papers that I was showing in the beginning. And so again, you have to define some notion of non-singularity of times, and then you have to use some like algebraic construction to prove that basically the key thing is that the number of points at which bad things happen, or at which you can't apply the implicit function theorem, let's say, is finite. So you can't have like a positive set of times in which in which you can't apply the implicit function theorem. So under this hypothesis of a non-singular time, then you have only the first three type of points that I showed you. So this basically is the conclusion. So again, yeah, this is just proof that I hope I maintain my promises. So yes. So again, the main contribution of this work was defining these 6 type of points, and then proving that there are no other type of points that can appear. So this looks maybe a bit kind of tautology, let's say, tautologic, but it was some extra work that one needs to do to really prove that, or to imagine also what could happen. And yes, I guess this ends my talk. So thank you, and if you want to have any questions, I can take it.
Thanks. Question? All right, then I will ask a question. So I'm not well versed in this field of semidefinite programming, but what I imagined from the time component is that the program can change through time.
Mm-hmm.
But what I saw on your pictures was that basically the optimization function turned, or the solution to the curve that you had was on the surface of the thing, right? And it was traveling like this. So I wonder whether this is just to make the example nice, or whether it is possible that the shape changes.
Yes. Okay. Thanks. That's really good question. Yes, indeed. These were exactly what you said, as you said. Like these examples were both the examples were both to be as simple as possible, and also to really provide, because I also had to provide an example of each type, because then I define the type and the type doesn't really exist, doesn't make sense. So these were also to try to provide the easiest example of that. But then it can happen that the feasible set changes as well. So the feasible set is the region, and the region can also move. But basically, if you go through the proof, let's say it's not really depending on, like you can also have a set that is moving and still the same thing happen. But actually, you're right. Like this was one of the most, because like it was a bit hard to imagine what was happening. So then I really had to kind of both use imagination, but then also like look at work that has been done on time. On set valued maps, and there are some results that were some classical results that were at the basis, and somehow these results still gives you the same results that I have, even if your feasible set that is time dependent.
Then I have another question. The last case you had this classification into 6 types or so. And yeah, this last one, there's probably no nice picture that would somehow illustrate this, right? Because the other ones you always had something, some simple example, but this seems like...
Yes, and this is actually very corner case. So I have some conjecture here, that is so you see here the parameterization was very like I really created a ad hoc example to have this crazy behavior, and I used like trigonometric function. So the question is, or the conjecture is, if the parameterization is polynomial, then probably this case would not happen. So these are very like corner cases, let's say. Yes, I also had a picture. Maybe I can find it later. With so here at each tk there is a continuous bifurcation, but you can still using trigonometric functions easily find cases in which you have loss of inner semi-continuity. Maybe actually Do we have a pen or?
Yeah.
There. Well, basically the same thing, but you have something like this. Maybe. So so now the solution is non-unique, and then you can do some crazy thing like this, and then then it's an accumulation point. So you see, like here the solution is unique, then suddenly became, and it's just made by, if you have like let's suppose that you have your feasible set is just this segment, and then you have an oscillating objective function, then it would it will stay here, and then it will become the whole segment. And I mean, you can construct such examples, but again, as you pointed out, it's the corner cases.
Thanks. Any other questions? Yeah. All right. So let's finish the speaker again.